Hello, hello. Hope you're all doing well today. Get started. I'm going to do one more dimensional analysis problem, and then we are going to start to move into chapter 2. And then just looking forward. So chapter 2 will start today, and then we'll finish it up next week. Then we'll have, you'll have your first test on the range will be Sunday, Monday, after next week. Okay. But once you get started, like you have an hour and 15 minutes, so you don't have 2 days to take the test. So find yourself a good time that works for you. You can sit down quietly and do it. All right. Let's see, what do I want to do here for y'all? Okay, so how many centimeters cubed are in 15.9 liters of H2O? All right. So in looking at this problem, setting ourselves up for success by figuring out what the given is and what we're trying to find. So we're given that we have 15.9 liters, and it says specifically of H2O. In this case, it doesn't really matter that it's H2O, but we're trying to find centimeters cubed. This and this are both units of volume. So you know you're going to want to be using conversion factors that have to do with volume conversion. There isn't really a direct relationship between liters and centimeters cubed, but I can do liters to milliliters. And then from milliliters, we can go to centimeters cubed. Okay. So the relationship between liters and milliliters, 1 liter is equal to 1,000 milliliters. If you wanted to use King Henry Dyed and hop, you can hop as well. And then the relationship between milliliters and centimeters cubed, we know that 1 milliliter is equal to 1 centimeter cubed. That's a direct relationship there. So start with my given 15.9 liters of H2O. I'm going to convert this into milliliters. So for every 1 liter of H2O, which I put on the bottom so that it cancels, I end up with 1,000 milliliters of H2O. And then we know for every 1 milliliter of H2O, it's equal to 1 centimeter cubed for H2O. Cancels, cancels. So we really only have to just move the decimal over 3 spots, or 15900 centimeters cubed will be our final answer. One thing I do want to talk about is how you can derive like cube relationships. So for instance, let's say that internet connection is unstable. Given that we know the relationship between inches to feet, right? And we're trying to find cubic inches to cubic feet. Okay, we want to find the relationship between.
We didn't get the problem.
Hey, did I lose you guys there for a minute? Yeah.
Yeah.
Okay. Let's go back to share screen and we'll start over, okay? Okay, so we're looking at this here. So we know the relationship between inches, feet, and feet. And I want to figure out what the relationship between inches cubed and feet cubed are. Just because we know that we get 12 inches for every 1 foot, right? But let's say the problem is how many inches cubed are in 2.4 feet cubed. Okay, so we're dealing with a volume relationship. And you don't know the conversion factor between inches cubed and feet cubed off the top of your head. But you do know the relationship between inches and feet, right? It's pretty basic, 12 inches for every 1 foot. So we can actually derive this relationship from this thing right here. So the way that we're going to do that is we're just going to cube it out. So so I'm going to take this to the 3rd power, and then I'm going to also take this side to the 3rd power. Okay. When you do this, you want to put the whole thing in parentheses. That third power will get distributed to the 12. It's also going to get distributed to the inch. Same thing with the third here. It's going to get distributed to the 1, and it's going to get distributed to the foot. So if you plug in 12 cubed in your calculator, we end up with a pretty big number, 1,728. And then we want to write inches cubed, because remember the 3 goes out here as well, is equal to, well, does anyone know what 1 times 1 times 1 is? It's just 1, right? 1, but it's not foot, it's 1 foot cubed. So this original thing without the cube was saying, hey, 12 inches of length is equal to 1 foot in the length. We've now derived that if we have a 1 foot by 1 foot by 1 foot box, it will contain 1,728 little inches cubed boxes, okay? So we were able to get this from this. The same thing is true if you have a relationship between, let's say we have 1 meter equals 100 centimeters, and we wanted to get the cubic relationship, we could just cube both sides and get 1 meter cubed is equal to 100 times 100 times 100, or a million. So 1 point, scratch that. 1 point, we won't even put the point. 1 times 10 to the 6 centimeters cubed, okay? So now we can go back to this equation that says, or this problem here that said, how many inches cubed are in 2.4 cubic feet? We can use this conversion factor now. We start with our given, which is 2.4 feet cubed. We're trying to find inches cubed. Start with our given 2.4 feet cubed. You can't use this one. You have to use this one, right? Because it's to the 3rd power. So we know for every 1 foot cubed, we end up with 1,728 inches cubed. The foot cubed will cancel, and we take our 2.4 and multiply it by the 1,728. We end up with a value of 4,147.2 inches cubed. This is an exact ratio, so we don't use this as far as our sig figs are concerned. This is a limiting, right? We only knew to the 10th place. So 2 sig figs, so I get to keep the 4, I get to keep the 1, the 4 tells the 1 to stay. So 4,100 inches cubed. So just sort of a nifty way to get these if you don't have them on hand, right? So if you come up to a problem that is dealing with volume and you're like, oh, I don't know the relationship between meters cubed and centimeters cubed. Well, you can find it if you know what the relationship between meters and centimeters is. You just cube them out. Any questions on that? So the guided notes that's in, I'll share here. Where is it? Moodle has some additional practice problems. That'll be probably be helpful for y'all. So if you want, you can go down here, guided notes, and then there's actually guided notes that are filled in. So you can use these if you need some additional help with dimensional analysis.
Before we step away from dimensional analysis, are there going to be examples in the guided notes of, or could we maybe do an example of, maybe would we ever have a problem where it's like centimeters cubed transitioning to feet cubed, or something where we're going from like the, you know, the
British
standards to the
British to the metric?
Mm-hmm.
Yeah, we can do one. Let's do it. Why not? Okay, so Let's do how many centimeters cubed are in 1.8 times 10 to the 6th, let's do 7, to the 7th inches cubed. So again, that little caret is just letting you know that it's going up. Okay, so how many centimeters cubed are in 1.8 times 10 to the 7th inches cubed? And so I'm gonna, I'll give you just a little assistance in that we do know that 1 inch equals 2.54 centimeters. Okay, we do know that. So I want you to come up with the relationship, the conversion factor of inch cubed to centimeter cubed, and then solve for the problem. Okay. So here we're given information 1.8 times 10 to the 7th inches cubed. We want to find centimeters cubed. So sometimes you can find this relationship right off the bat. If you don't, you can always derive it from the more basic 1 inch equals 2.54 centimeters by cubing both sides. And what we end up getting is that 1 inch cubed, because the 3 distributes to the 1, so 1 times 1 times 1 is 1, inch cubed is equal to 16.387. So I'm going to go with 16.39. centimeters cubed. Then you just get to use this conversion factor like you'd use any other one. So we start with our given, we have 1.8 times 10 to the 7th inches cubed. And in this case, I'm going to throw my inches cubed on the bottom. So the 1 inch cubed sits on the bottom. The 16.39 centimeters cubed sits on the top. So let me plug that in. All right, and I ended up with 200. We got 2 sig figs coming off of our given. So it's, I would say 295 if I had 3 sig figs, but I only get to have 2 sig figs. So it's really going to be 3.0 times 10 to the 3 to the 8th centimeters cubed. Questions on that?
Yeah, I guess my question would be like, if it's 2 sig figs, we're not using the third figure to round up to the second?
So I had, my answer was 295,020,000. Yeah.
My answer was 29496, but I think I just used,
I
I didn't round it up.
So you didn't round this number here. So yours is actually probably more correct than mine. So if you got that answer out, then you would keep it as 2.9. Okay. And that would be fine. Yeah. That's sort of a splitting hairs thing. We're not gonna, you'll be okay on the exam with that. Okay. I rounded here because I didn't plug it in, rounding errors. So I ended up with 259. So the 5 told the 9 to go up. So, okay. Any questions on that, on how you can derive? You could do it for area too. If you had area, you could solve for area from the single digits. No, I didn't use sig figs. I just used being lazy. I didn't want to write the whole thing out.
Could you go over how you got that number?
This number, 16?
No, the number that was like the answer before you put it into the exponents and all of that. Yes.
How did you get 3.0 times 10 to the 8th, I think is what she's asking.
Yeah, that's what I'm asking.
How did I get this?
Mm-hmm.
So I had this number in my calculator, yeah?
Mm-hmm.
This has 2 significant figures, so I can only honor 2 sig figs. So I keep the 2 and the 9. The 5 tells the 9 to round up to what? 10, which rounds the 2 to a 3. So it ends up being 300,000,000,000. I wrote it in scientific notation because this is significant and this is significant. And I wanted to represent that to the reader. So I wrote it as 3.0 times 10, and I hopped 1, 2, 3, 4, 5, 6, 7, 8 hops.
Okay, that makes sense. Thank you.
Yeah, no worries. Any other questions? No. Okay. So let's get out of math for a little bit. We'll leave math for a little bit and we'll go to some concept stuff. All right. No, we don't want to do chapter 1 again, do we? There we go. All right, so chapter 2 is going to be all about atoms, molecules, and ions. I would definitely recommend at this point in the semester getting yourself a periodic chart. You can either print one out or there's one in the textbook. I have one, like a plastic one, table like a table mat for my daughter that I gave to her so she can learn the elements. And I use that one pretty regularly. That one's nice. I got it at Michael's for like $2. But you're gonna wanna have a periodic chart available because you are going to use that thing all the time. All right, so by next week, get yourself a periodic chart. You can print a free one off the internet if you want to, but I want you to have one in hand, okay? If you're fine drawing in your book and writing in your book, you can use that one too. So atoms, molecules, and ions. So the atomic theory of matter. So there were Greek philosophers back in BC, like a long, long time ago, that came up with this idea of the atom, or they referred to it as the atomos, which meant uncuttable. And so they believed that all of nature was made up of these particles that were indivisible or uncuttable, or these solid little balls, which you can sort of think of as, they thought of it as the atom. Experiments in the 18th and 19th century. So, I mean, this was back in BC, so like almost 2,000 years later, they start playing around with the idea in a little bit more detail. And specifically, John Dalton comes up in the early 1800s with 3 things that are sort of the backbone of modern chemistry. There is also a periodic table in the back of the lab manual. Yes, lab manual should have one too. Yeah, so you can rip that one out and draw all over it. So 3 things that Dalton, well, there's really 4 postulates, but this page has 3 of them. The law of constant composition, which we talked a little bit about, the law of conservation of mass, and then the law of multiple proportions. So we'll look at each of those in detail. So again, law of constant composition. We discussed this in chapter 1. Compounds have a definite composition. That means that the relative number of atoms of each element in that compound is always the same. It's one of the basic laws of his theory. So as far as an example, CO2. The relationship in CO2 is 1 carbon for every 2 oxygens. That is what makes CO2 CO2. If we instead we were dealing with the more nefarious carbon monoxide, CO, that's 1 carbon for every 1 oxygen, okay? This ratio has to stay the same within a given compound. So if we're dealing with CO2, whether you have 1 molecule of it or you have an entire room of it, you will always have this ratio. That is the law of constant composition. Composition is consistent within the compound. Law of conservation of mass. So if you've ever taken a physics class, you may have heard of this, but the total mass of a substance present at the end of a chemical process is the same as the mass of the substances present at the start. This was discovered by Lavoisier. This is another law in Dalton's theory. So an example of this, or a couple things to highlight. This is only talking about chemical processes, okay? When we're dealing with nuclear reactions, we actually will get a change in mass. So in nuclear reactions, we can take mass and convert it into energy. So we can lose mass. So the law of conservation of mass only applies to chemical processes or chemical reactions. So let's say we're going to combust methane. So methane is CH4. I'm combusting it with oxygen, which is O2. And I produce CO2 and H2O. We will get into how to write these later on, so don't be scared of this. It's just an example. What I'm going to do now, though, is I have to balance this equation, because if I look over here, I have 1 carbon, and I have 1 carbon on this side, which is good. Here I have 4 hydrogens. Over here, I only have 2 hydrogens. So in the way it's written now, 2 hydrogens have sort of just disappeared. That does not follow this mass consistent or conservation of mass. So I'm going to put a 2 in front of here. And then I'm going to I have 2 oxygens here, and I have 2 oxygens here, and then I have an additional 2 oxygens here. So I'm going to put a 2 here. So now that I have the same number of atoms that I started with is the same that I'm ending with after the reaction. Another thing we could say is that if this is 36.4 grams of methane and oxygen, then CO2 and H2O must also equal 36.4 grams. These two things have to equal each other during a chemical process or a chemical reaction. The law of multiple proportions. So if 2 elements, A and B, form more than one type of compound, the masses of B that combine with a given mass of A are in the ratio of small whole numbers. So it always has to be in a whole number ratio. We don't have half atoms. John Dalton discovered this law while developing his atomic theory. This is an important part of it. When 2 or more compounds exist from the same elements, they cannot have the same relative number of atoms. So let's go back to our carbon dioxide and our carbon monoxide, CO versus CO2. So if you have 2 or more compounds, so this is compound 1 here, and this is compound 2 here, they're composed of the same elements, right? They're both carbon and oxygen, but they do not have the same number of atoms. This one has 1 carbon and 1 oxygen. This one has 1 carbon and 2 oxygens. If we had something like this, CO versus CO, we're no longer talking about 2 different compounds. We're talking about the same compound, right? So that doesn't work. So this is sort of common sense, but know with this thing here that these subscripts that are letting us know how many we have of each of the atoms, that always has to be a whole number rate. Relationship. We're never going to have CO 1.5. We don't have half atoms, so no good on that. So postulates of Dalton's atomic theory. Each element is composed of extremely small particles called atoms. So any element, whether it's gold, aluminum, whatever, can be broken down into these tiny things called atoms. So here's an atom of oxygen, and here's an atom of nitrogen. The atom is the smallest identifiable material of that element. So if I was to take an element and cut it in half and cut it in half and cut it in half to its most fundamental thing, it would be an atom of that element. If I cut this thing in half, an atom in half, then I start getting into protons, neutrons, and electrons. Protons, neutrons, and electrons in here are the same as the protons, neutrons, and electrons in here. They're just in different proportions. Second thing, all atoms of a given element are identical, but the atoms of one element are different from the atoms of another element. So every oxygen atom is going to have identical properties. Every nitrogen atom is going to have, again, similar chemical properties, similar number of protons, but these guys will be different from these guys. These do not equate to each other. If I change the number of protons, they become a different material. Number 3, atoms of one element cannot be changed into atoms of a different element by chemical reactions. Key thing here, this, by chemical reactions. Atoms are neither created nor destroyed in a chemical reaction, okay? So again, within a chemical reaction. If we're doing a nuclear reaction or nuclear chemistry, we can see atoms actually changing into something different. And then number 4, compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. So we've got nitrogen and oxygen. These are elements. They're not bonded together, but then we somehow bring them together or bond or smush them together, and we get nitrogen monoxide. This is the compound. In order to be nitrogen monoxide, you have to have 1 nitrogen and 1 oxygen. That is its recipe. We can think of a compound or its chemical formula as its built-in recipe to making it. So we went over this, we did this one. All right. So back in the early 1800s, this sort of first modern day idea of atoms under Dalton's view was that they were the smallest possible particle. So we didn't have anything tinier than an atom. It was this hard, indestructible ball. Many discoveries led to the fact that the atom itself was made up of actually smaller particles. So we can actually take an atom and break it up into smaller things, specifically protons, neutrons, and electrons. So things that led to that: electrons and cathode rays, radioactivity. Right, radioactivity wouldn't be possible if there wasn't something smaller: nucleus, protons, and neutrons. Let's move this out a little. So electron and a cathode ray. So streams of negatively charged particles were found to emanate from cathode tubes, causing a fluorescent quality. So we'd have a cathode tube here, and we'd find right here, we can see in the center there, this is a stream of negatively charged particles. The reason that we know it's negative is because we can put a magnet on the outside of it and it will actually deflect it. All right. We use the positive side of the magnet, we find that there's deflection. So J.J. Thomson was credited with discovering that there was a negative particle within our, what was traditionally just a solid atom. So Tom, you don't need to know this, don't worry about that. Okay, so once we had the charge mass ratio of the electron, we can move on from that. Okay, so let's talk about radioactivity. So radioactivity is the spontaneous emission of high energy radiation by an atom. So when we have an atom, at some point it can, if it's unstable, it can release a bunch of energy in a couple different forms, alpha, gamma, and beta rays. It was first discovered by a man, but Marie Curie was a big component of the discovery of radioactivity. There's actually a movie coming out about her. And its discovery showed that the atom and more subatomic particles and energy associated with it. So when we saw the properties of radioactivity, that there was this emission of different types of smaller particles, we knew that the atom couldn't just be some solid sort of inert material, that it had to have more going on than that. So as far as radioactivity is concerned, there's three types of radiation. We have alpha particles, we have beta particles. Beta particles are sort of like electrons. Alpha particles, an alpha particle is a positively charged particle. It's pretty much like a helium atom. We've got our beta particle, and then we've got our gamma ray, which is uncharged and very, very high energy. So gamma radiation, this is what comes off of things like nuclear explosions. The rays of stars are a lot of gamma radiation, or gamma rays. So J.J. Thomson, the guy who discovered that string of negative electrons, he came up with this theory called, it's kind of a silly name, but it's called the plum pudding model, because the electron itself was actually discovered before the nucleus or the proton. So at this point, J.J. Thomson knows that the atom has negative electrons in it. But he knows that overall, the whole atom is neutral charged. So something has to counteract this negative electron. So he thinks that there is this sphere or cloud of positive charge. So there's these little negative electrons floating out around in a positive cloud, and they balance each other out to give us the overall neutral charge. Obviously now that sounds ridiculous because we know about the nucleus, but they didn't know about the nucleus then. So that was the best they could come up with. So later on is when they discovered the nucleus. So Rutherford had what's kind of known as his classic gold foil experiment. So he took a source of alpha particles. I think it was like some sort of radioactive or decaying lead. And this thing shot out a beam of alpha particles. And when the alpha particles went through it was a really thin piece of gold foil, like just a couple atoms thick, super, super thin. So he sent this alpha beam through, and if we were going off of the plum pudding model, what we would expect is that those alpha particles, because they're so high energy, should just go straight through. Every single one should just go straight through, okay? But that's not what he found. What he found was that some of them went straight through, and then some of them got deflected. So they moved a little bit to the side, and some of them actually like went back in the opposite direction. He had this fluorescent screen that when it got hit with the particle, it would light up. So some of them were going straight through, but other ones were pinging off in other directions. And so what he realized is that something has to be deflecting these alpha particles, and it has to be pretty substantial in mass. The electron is not big enough to deflect something like an alpha particle. So we've got this thing coming through here, and it's getting deflected. It's hitting something. So what he came up with was this thing in the center of the atom known as the nucleus. So this led to the nuclear atom, or the nuclear view of an atom, or the idea that we've got an atom and in the center of it is a nucleus, and then there are electrons sort of hanging out or floating around it. So he said that the nucleus was an extremely dense positive center with the electrons around the outside. What we ended up finding was that actually most of the atom is empty space with a very small amount of mass in the center, and then the electrons, which are so teeny tiny, they take up very, very small amount of mass. The interesting thing about matter is that from a human scale, we look at material, we look at matter, and we think of it as being this sort of solid, continuous, like real thing, right? But when we break it up into smaller pieces, we find that our matter is actually made up of mostly empty space and a little bit of mass. And actually, if we break up the nucleus, it's made up of protons and neutrons, which are a lot of space, and then a proton, let's say. And if we break up a proton into its fundamental particles, it's actually made up of mostly empty space and a very, very small amount of mass in the form of quarks. And one theory, string theory, says that if we were to break up our quarks and things like that, that it would be made up of empty space and just a vibrating ring of energy. So the idea that there is no matter at all, that all matter, every atom of every person and every star and every galaxy is all made up of vibrating rings of energy. So there's your existential crises for the afternoon. We'll leave it at that. So some characteristics of these subatomic particles. Protons have a positive charge, super important, protons positive. Electrons have a negative charge, and then neutrons, kind of no-brainer, those are the neutral ones, okay? As far as their size is concerned, protons and neutrons have almost the same mass. We kind of give them the mass of 1. The mass of an electron is so small that we usually don't include it. We just say that it's 0. So here are the masses in relationship to a value known as AMU. So a proton is 1.0073 AMUs. The neutron is 1.0087 AMUs, very, very close to each other. The electron, super teeny tiny, right? On a scale of 10 to the -4th smaller. So the electron, not really any mass, but it does have a negative charge, so it's got a big bang for its buck. Tiny, but powerful. Neutrons, big, but as far as charge is concerned, they don't do a whole lot. Protons, large and with a charge. So the atomic number, how do we determine which element an atom is? So let's say I have an atom and it has 6 protons floating around in it. That would be its atomic number. The atomic number is the number of protons that lie within the nucleus. Because an atom has an overall neutral charge, the number of protons should equal the number of electrons in a ground state atom. So let's say I have an atom and it's got 6 protons in it. It should, as long as it's not charged, should also have 6 electrons. The atomic number, or the number of protons, is what determines what the material is. All right, so if I have 6 protons versus 7 versus 8, those are all going to be different types of elements. So when writing out my symbol here, this is carbon. It has 6 protons. Its atomic number is 6. If I put the mass on the top here in the upper left-hand corner, this is the number of protons plus the number of neutrons. So one equation, real basic equation, your mass is equal to your protons plus your neutrons. So in this case, my mass is 12. My number of protons is 6. So my number of neutrons must also be 6 for this given one. This can change. You can have carbon 12, you can have carbon 13, you can have carbon 14. Those are known as isotopes. We'll talk about that in a little bit, but the number of neutrons can change. The number of protons cannot change. If this number changes, it's no longer carbon, okay? It becomes something new. So elements will always be represented by 1 or 2 letter symbols, for which the first letter is always capitalized. So for carbon, it's C. All atoms of the same element have the same number of protons, which is called the atomic number. It is written as a subscript before the symbol sometimes. Sometimes they don't write it like that. So you won't always see carbon as carbon 6, okay? A lot of times you just see it written as carbon. Why? Because those 2 numbers, or this number and this symbol, are synonymous with each other. You can't be carbon and not have 6. The mass number is the total number of protons and neutrons in the nucleus, and it's written as a superscript before the symbol. So you'll see it in the upper corner here. So we'll talk about a little bit more about isotopes farther on down the line. Okay, so when looking at an isotope, and isotopes are the same type of atom, but they actually have a different mass. So here I've got carbon 11, carbon 12, carbon 13, and carbon 14. So if we're calculating protons, electrons, and neutrons, if I know that it's carbon, I right off the bat can say every single one of those things will have 6 protons. Because if it is carbon, it has to have 6 protons. None of these are charged. There's no thing in the upper right-hand corner saying it has a 2+ charge or a -5 charge or whatever. So we know that the number of protons and the number of electrons have to equal each other, right? Because our overall element is neutral. So 6 positives, 6 negatives. The only thing that's shifting in this case is the number of neutrons. So if my total mass is 11, 6 of them are being taken up by protons. That means the remaining 5 are the number of neutrons. If we're dealing with carbon 12, we have an atomic mass of 12, 6 are protons, 6 are neutrons. If it's carbon 13, 6 are protons, 7 are neutrons. If it's carbon 14, our really heavy carbon, we have 6 protons and we have 8 neutrons. Most of the carbon found in nature is carbon 12. Okay, like 99% of it is carbon 12. We do have a little bit of the other ones, carbon 14, or if you've heard of like radioactive carbon or radioactive carbon dating that they use to date, like anthropologic things, pots and stuff like that. They'll use the decay of carbon 14 because it's unstable. Isotopes are these things, just really quickly, are really cool. I think isotopes are probably one of the coolest things that you can have in chemistry. There's 2 types of isotopes. There's radioactive isotopes. So this one here would be an example of a radioactive isotope. Means that it decays into something else over a given amount of time. So you can use it to age things, which is cool. Then we have like something like carbon 12, which is a stable isotope. And that's what I've studied for my master's was stable isotopes, not of carbon 12, but of oxygens and chlorines. And what's neat about stable isotopes is that they are stable. So they don't change even when they run through a bunch of different processes. So you can use these to fingerprint a lot of different things in the environment. An example of that would be, what are some things that they use it for? Well, the way I used it was I was testing perchlorate contamination in the Great Lakes. And so I was trying to see if the chemical that was in the Great Lakes was coming from a company. And what you can do is you can fingerprint the ratio of stable isotopes in what the company is dumping out of their drain pipe. And then you can sample it in the water. And if that ratio is the same, you've proven that they in fact did the polluting. Another thing you can do, they have done this before with oxygen 16, oxygen 18 ratios. So they can trace things like where marijuana is being grown. I guess now it's not a big deal anymore, but back in the day, they used to trace where marijuana was grown. And because marijuana absorbs water from the raindrops, rain contains oxygen in it and from the H2O. And if it's closer to the shoreline, it'll have a certain sort of ratio versus if it's inland. So they could determine, hey, this marijuana was grown by the shore near the equator. They also used stable isotopes for looking at different ways of like ancient mummies in people's lives, like how they lived their lives. So they would take their hair, which mummy hair wasn't very sought after, but now they know that they can take mummy's hair and they can actually chronologically look at the carbon isotopes, stable isotopes in the mummy's hair and determine what type of food they were eating, determine if they were nomadic, determine if they had some sort of cyclical pattern to their migrations, all this cool stuff. So I like stable isotopes. So if you ever want to talk stable isotopes, we can talk stable isotopes. Radioactive isotopes are really cool too, but I like stable. Okay. So the AMU, or the atomic mass unit. So atoms have a very, very small mass. The heaviest known atoms have a mass of 4 times 10 to the negative 22 grams, okay? So take that number and move the decimal to the left, 22. So very, very small. So as far as a mass scale, we wanted to come up with something, well, not we, but scientists wanted to come up with something that was, would take into account that teeny tininess. So they go off of what's known as an AMU. So 1 AMU is equal to 1.66054 times 10 to the negative 24th grams. That's the value of an AMU. And remember, 1 AMU is about the mass of a proton and about the mass of a neutron. Atomic weight. So, you know what? I think we are going to stop there for today. Yeah, we'll stop there for today. So we don't meet on Monday, so it doesn't matter. But know that your Monday classes are off because of Labor Day. So we will see each other on Tuesday. You do have a lab that's due on Sunday, so maybe try and get that done sometime today or tomorrow, and then you can ask me questions. Otherwise, you are free to go. Have a really good weekend and a good Labor Day break. Stay safe, and if you have any questions for me, please feel free to hang around and we can chit chat. Okay. Otherwise, bye bye. Hold on 1 second.